Okay, so we're going to have a look at the latent heat of fusion of ice. This is an experiment that normally I would expect you to do in the lab, but of course circumstances have intervened. You saw my glamorous assistant there, Mr. Baker, holding up the table that I plan to use. You can see I've got a stop clock in the background. The only reason for the stop clock in the background is that I might jump ahead in the video, and so it's just so that you can keep an eye on how the time is running. We aren't actually going to use time in this. Only two columns are energy in kilojoules and temperature in degrees C. So I have a can. I have a can with some insulation in that I've been cooling down, and having got that properly cold, I'm now going to tip that away and put some freshly ground ice in. I don't know whether you could see there, but the ice is already quite wet, so the ice will be at 0 degrees C. Whether our thermometers agree that the ice is at 0 degrees C will be interesting. How bad the zero error on our thermometers are. Mr. Baker is enjoying himself, teasing me with his yellow pen. This is a thermocouple. Now, thermocouples are on the course, so we'll come back to thermocouples later on. But I'm hoping this one, which is showing up on this screen here, I didn't do that with a yellow pencil, Mr. Baker, on that screen there, will be the more accurate of the two. Let's see what happens. Meanwhile, I have over here an immersion heater. This is a 12-volt immersion heater designed to go into liquids. So we've quickly sorted out the problem with the thermocouple. The previous thermocouple was causing us problems, but this one's reading about right at about 0.6 of a degree C. I don't know if you can read this one, but that's reading at minus 0.5 degrees C. So if we took the average of the two of them, we'd have bang on what we wanted, which is the problem of using thermocouples without a decent zero reference, which is one of the things we will talk about when we do thermocouples a bit later on in the course. So my joule meter is on, ready to go. I'm going to put my immersion heater into the ice. And I'm going to get it all going. And what I'm going to do is I'm going to take a temperature measurement every kilojoule. And my glamorous assistant missed completely there. There you go, glamorous assistant's got it this time. So every kilojoule I'm going to take a temperature measurement, and we're not far away from the first one. So 0 was 0.55 and 1 kilojoule is 0.55. Just have to keep stirring it so that it's not just the ice around the immersion heater that is melting. So 2 kilojoules, 0.53. It does take a long time, this experiment. I'm just coming up to 3 kilojoules, 0.54. Four kilojoules is 0.51. So you just have to think a little bit about what we're doing here. We've just put 4,000 joules of heat energy into this system. It's not made the slightest bit of difference. Just move my immersion meter around. You see, it is working, because you see this. You might be able to see on the video there the steam coming off as I gave it a stir. So we are definitely putting heat in there, but it's making no difference at all to the temperature. There you go, 5.55. Coming up on 6. 6 is 0.53. Now when we do this as a class practical, normally by now somebody's put their hand up and said, "Sir, my thermometer's broken." Because I get you guys to do this with liquid in glass thermometers rather than these electronic ones. And somebody always says, "Sir, I've got a broken thermometer because I've now put in 7 kilojoules of energy and my temperature has barely changed." Oh, and we might have a bit of a change here. 7, we've got 0.6. Probably just means the ice in direct contact with my thermocouple is melted and I need to give it a stir. Hopefully you can see on the video when I stir it, there's a little bit of steam comes off, because what happens is the immersion heater melts a little gap around itself, and then that little air gap insulates the immersion heater from the rest of the ice, so the immersion heater starts to get hot, and then when I give it a stir, the ice goes back in contact with the hot immersion heater and melts, and just a little tiny bit steams off. And I missed 8 there, but it ain't gone very far, is it? 0.6. Just coming up at 9. Oh, look at that. We might have a change. Just coming up on 9 and 0.96. Oh, look at that. Temperature's gone up. It's probably because I've moved the thermocouple out of the water. Put the thermocouple back in. Oh, look, gone straight back down again. I was excited for a second there. Something happened. 10. Just approaching 10. 0.51. So we know that that last reading must have been an anomaly, because where I managed to knock the thermocouple so that it was no longer sitting tightly in the water. So when we plot our graph, we wouldn't put our line of best fit through that one, but we would still put it in the data. $11.50. Coming up on 12.49. $13.50. Now a lot less ice in there now, starting to be the majority is water. $14.6. $15.62. $16.84. 17.72. Jumped up a bit, 0.99. Just going to give it a proper stir. Just heard Mr. Marzan pop in to see what I was up to. So give it a proper stir, try and mix the ice that's left up with the water, brings the temperature down to 0.66 for 19. $20.99. Now I hope you're amazed by this. That's 20,000 joules of heat energy that we've just pumped into this little tiny can of ice, and we haven't melted all the ice, and we've barely done anything to the temperature. Temperature's gone up and down really depending on how close the thermocouple is to the immersion heater, and not really in response to the ice itself changing temperature. We're still at pretty much the same temperature we started at, 21.7. And 22.99. $23.94. Right, I'm just going to see if I can move the camera smoothly so that you can actually see how much ice is left. So you may not be able to see, but you might be able to see the glitter of the ice. So we've still got some ice floating on the surface in there. The bulk of that is water. And I missed 24 there, but that would have been 0.60. And 25.70. You hear the rattle of the ice. You can see a little bit of steam as it's touching the top bit of the immersion heater, which is a lot hotter than that bit that's in the water. Hopefully you can hear the ice rattling in there. $26, 1.16. $27, 1.53. You see the temperature's starting to go up now. I've still got some ice in there, so really the temperature shouldn't be going up, but it's very difficult to keep it perfectly stirred. And if you don't keep it perfectly stirred, it won't all stay at an unchanging temperature. So I'm trying to stir it and keep it all in equilibrium, but it's hard. 28, 1.46. Almost no ice left now. 29, 1.92. And that's almost it. Ice is almost gone at 30,000 kilojoules. Sorry, 30,000 joules. That's 30,000 joules is 2.56. Head boy's just popped in to ask a question. Just coming up on 31. 31 is 3.17.
What do you want us to do about the board? How should we set it up if we're splitting it in?
Well, you can give me the things as individual blocks, and I'll format it. But if you can give me enough blocks to fill that space, then I'll format it up in Photoshop.
So just sort of like Word documents in that.
Anything you want to do it in, basically.
Pictures.
32 4.16.
Fine. So similar size to the one on the left. Yeah.
Exactly that. Make sure the picture of all of you guys with the kit.
You can put pictures of us and the kit.
33 5.90.
Yeah, that's fine. Right. Cheers, sir.
Goodbye, head boy. So the ice is completely gone now, and the temperature is starting to shoot up. So 35, sorry, I missed 34 there, and 34 would have been 7.1. And 35, 7.53. Thirty-six, 9.95. $37, 11.26. Even if you can't see, I hope you can hear that the sound has changed. There's no longer any ice rattling in there. And you can definitely see it now that we've lost the ice. The temperature is really shooting up. So 38 is 13.82. $39, 15.71. $40, 17.72. Probably going up about 2 degrees C every kilojoule now, isn't it? $41, 18.63. 42, 21.909. Sorry, that was 21.09. I'm going to go until it gets up to 30 degrees C so that we get a decent graph. So hopefully not too many more measurements now. 43, 21.10. Seem to have plateaued out. I wonder why that is. Oh, so I haven't stirred it properly, that's why we've plateaued. So 44, 24.25. So 43 was an anomaly. Oh, Mr. Smith wandered in, see what I'm doing. 45, 26.10. Hopefully only a couple more measurements. So 46, 27.86. Right, sir.
Yeah.
So I just find this experiment astonishing. There's a tiny amount of water we've got in there, and we've had to put in 47 kilojoules, 29.44. 47 kilojoules to get its temperature to go up by 30 degrees C. It's an enormous amount of energy. And we'll do one more, go to 38. And 48 is 30.67. Right, I've come into the STEM lab because it's got a really good set of scales easily available to me. Of course, if we want to work out the specific values of either latent heat or specific heat capacity of water, then we need to know how much energy per kilogram, because that's what specific means. It means per kilogram. So I've got to know how much water we actually melted. So I'm just going to quickly sort that out. So I'm just going to zero my scales. There you go. The amount of water we melted was 98.43 grams. So to work out the specific value, we will have to divide by 0.09843 to turn it into a kilogram.